The quantum revolution, a breakthrough that changes everything. A seismic shift in computing has just unfolded. A new superconducting quantum processor has achieved something once thought impossible, solving a problem in mere seconds that would take the most powerful supercomputer on Earth an unfathomable 6.4 billion years. This isn't just an advancement, it's a paradigm shift. And here's the real shocker. It surpasses Google's Sycamore processor by a factor of 1 million. But what makes this new technology so groundbreaking? How did researchers achieve this milestone, and what does it mean for the future of computing? Let's dive into the details of this astonishing breakthrough. A leap beyond quantum supremacy. Quantum supremacy, the point where quantum computers outperform classical ones, has long been a milestone pursued by scientists worldwide. Google made history in 2019 with its Sycamore processor, a 67-qubit machine that completed in 200 seconds what would take a classical supercomputer 10,000 years. Now, a new quantum processor has shattered that record, exhibiting computational prowess on a scale never seen before. At its heart, this processor leverages 105 superconducting qubits arranged in a precise 15x7 grid, interconnected by 182 couplers to maximize computational efficiency. Researchers fine-tuned 83 qubits to perform a rigorous experiment, pushing the limits of stability and error reduction. The results? A processor that executes random circuit sampling, a notoriously complex benchmarking task, faster and more precisely than anything before it. Hit the like and subscribe buttons now. You don't want to miss the next video, and it really helps the algorithm so I can make more cool videos. Thanks. Now let's continue. But what does this mean in practical terms? Imagine a world where calculations that would have taken humanity centuries to process can be solved in a matter of moments. Quantum processors like this are laying the groundwork for the next era of computing, where problems in cryptography, pharmaceutical research, and climate modeling can be tackled with unparalleled speed. Precision like never before. Quantum operations hinge on maintaining precision, and this new processor excels in that regard. Single-qubit gate fidelity measures an astounding 99.9%, while 2-qubit gate fidelity reaches 99.62%. Such staggering accuracy drastically minimizes errors that have long plagued quantum calculations. Even Google's Willow chip, introduced in 2024 with the same 105-qubit capacity, cannot match the performance benchmarks set by this latest development. A fundamental challenge in quantum computing has always been decoherence, the loss of quantum information due to external interference. To combat this, researchers employed cutting-edge materials such as tantalum and aluminum, coupled with advanced flip-chip bonding technology. These innovations extend coherence times, allowing quantum states to persist long enough for intricate calculations to be performed with unprecedented accuracy. This is a significant leap forward because the Achilles heel of quantum computing has always been stability. Without extended coherence, calculations collapse before they can be completed. The fact that this processor has addressed these issues marks a major step toward functional, large-scale quantum applications. For years, the world's technological powerhouses have vied for dominance in quantum computing. The US, China, and Europe have poured billions into research, seeking an edge in secure communications, cryptography, and computational power. Now, with this latest quantum processor, the balance of power may be shifting. This development builds on previous milestones in quantum research, following advancements in superconducting circuits and photonic-based quantum computing. While early efforts aimed to establish superiority over classical systems, the next phase involves applying quantum power to practical fields like artificial intelligence, material science, and cybersecurity. What does this mean for national security? The potential of quantum computers to crack encryption in seconds has long been a concern for intelligence agencies. The race to achieve quantum dominance isn't just about scientific prestige. It has profound implications for defense, surveillance, and data protection. Whoever controls quantum computing will hold a significant advantage in digital warfare. Please take a second to smash the like and subscribe buttons now. You'll get notified when our next video comes out, and it really helps us with the algorithm too. Thanks. Cracking the code, the path to fault-tolerant quantum computing. One of the greatest challenges facing quantum computing is error correction. Even with near-perfect fidelity rates, quantum processors remain susceptible to minor errors that can cascade into computational failure. Google recently made strides in error correction with its Willow chip, leveraging surface code qubits to significantly reduce logical errors. But they are not alone. Global researchers are closing in on new architectures designed to stabilize qubits and make quantum computing more reliable. Beyond computation, quantum advancements extend into secure communications. The potential for quantum encrypted messaging, immune to hacking and interception, is rapidly becoming a reality. Quantum networks are already being implemented worldwide, linking satellites and ground-based hubs in an effort to create an unbreakable global communication system. But the leap from theory to practice is enormous. Fault-tolerant quantum computing, where quantum systems can run indefinitely without accumulating disruptive errors, is still on the horizon. Engineers are working on sophisticated quantum error correction techniques to bridge this gap. The more they refine these methods, the closer we get to seeing quantum computers integrated into everyday applications. Are we in the quantum age? While this new processor represents an astonishing leap forward, are we truly entering the quantum era? Not just yet. Despite its unmatched performance, real-world applications of quantum computing remain in development. The challenge now is transitioning from theoretical breakthroughs to practical applications, applying quantum processors to solve complex problems in finance, medicine, and logistics. One of the key obstacles is that many benchmark tasks, like random circuit sampling, are not inherently useful outside of proving quantum advantage. True impact will come when quantum systems can handle encryption, drug discovery, and materials research with tangible, real-world benefits. Another pressing challenge is scaling up. Quantum computers remain highly sensitive to environmental factors, requiring near absolute zero temperatures to function. Improving stability, reducing error rates, and finding cost-effective methods to mass-produce quantum chips will determine whether we witness the dawn of commercial quantum computing within the next decade. The quantum arms race intensifies. This isn't just a scientific achievement, it's a statement, a warning shot in the intensifying quantum race. The question is no longer whether quantum computers will change the world, but rather, who will harness their potential first. The US, China, and other nations are investing heavily, each vying for the top spot in this revolutionary field. If breakthroughs continue at this pace, the next decade could see quantum computing advance from experimental laboratories to global industries. Will the West's focus on error correction and large-scale architectures keep it ahead, or will aggressive research strategies elsewhere push the boundaries even further? One thing is certain, the quantum revolution is no longer a distant future. It's happening now, and the stakes have never been higher. If you found this deep dive into quantum computing fascinating, make sure to like, share, and subscribe for more insights into groundbreaking discoveries. Drop a comment below with your thoughts. Where do you think quantum computing will take us next? Thanks for watching, and stay curious.